Also need to record. Okay, now we're recording. Let me try this again. Share entire screen. Content only, so no, the whole thing. Sure. Okay, let's try this again. Okay, now can you see the whole picture?
Yes.
Okay, all right, perfect. Great, let me drag y'all over here. I think that's as far as it's gonna let me drag it. Great. Okay. All right, we're just gonna have to work around Bailey and Mia up there. So if I have to draw anything, I'll draw it around y'all. All right, here we go. All right, so amino acids. Sorry for our brief intermission there. Okay. Now we're gonna do amino acids. Does anybody have any lingering questions from water slash titrations or anything? Okay. Oh, a couple of other things. Your active homework should be live, so you should be able to see that now. Let me know if you run into issues when you do that. You have 20 attempts per question, but if you get to like attempt number 15 and you haven't gotten there yet, please come see me before you make it all the way to 20. Um, the key for the amino acid quiz is also finally up. Sorry that that took me so long. But anyway, it's up there, so you can see it. I've also been asked if you can do bond line structure. We'll hopefully get to some examples today where we're going to have to sort of draw out and manipulate some of the amino acids. So I think bond line might make that a little bit harder, but if that's how you need to memorize it, that's fine. For the quiz purposes, I don't care how you do it. As long as all the elements are there and they're connected in the ways that they should be, they'll be good. All right. Any questions before we get rolling? All right. Here we go. So the amino acids, yay. Hopefully, honestly, I don't know if I had seen these before I took biochem. So if you haven't seen them before, that's okay. I'm pretty sure the first time I ever really saw them was biochem. Um, so amino acid quiz. Unfortunately, you do need to know the amino acid structures. Sad face. I hated it when I was in biochem. I hate that I have to make you do it, but we unfortunately do have to do it. You'll need to know it for the ACS final. You'll need to know it for the MCAT. Um, and really to understand kind of as we're going through proteins and peptides and stuff like that, you do got to know their structures. So it's a unfortunately a necessary evil. I tried to not do it, but we got to do it. I think the slides that are on Canvas say September 9th because I put them up there before I updated them for this semester. That was for last semester. Yours is next Wednesday on the 10th. So my goal is for us to finish the slides Monday. Then we can take the quiz on Wednesday and then maybe do a little bit of recap review before I leave, before Brie and Ashley start taking over the new stuff. They will teach new stuff. Um, this is an aside. They're not going to teach stuff that's going to be on your test next Friday. I feel like that would not be fair. For me to have someone that's not me teach you new material that you're going to be tested on before I'm back to make sure it went okay. And that's generally how this will go. We'll finish material several class periods before you actually test on it. Just so you have time to, I don't want to like give you new material on Wednesday and then test you on it on Friday. That doesn't give you a lot of time to study or understand. So anyway, so yeah, your test is not this Friday. Not today is this Friday. It's not today. Yay. It's not next Friday, but it is the next Friday. So the material that you cover the next Friday with Bree and then the next Monday with Ashley, not going to be on your first test. Yeah.
You said you'll give us the test, the whole test.
Yes. Yeah. So this weekend I'm going to start working on the new test and I'll get the old test put up on Canvas. My goal is to have the test completely written before I leave so that we can do some structured, targeted review on Wednesday. So feeling good? All right. Amino acids, yay. Oh, good. Good, good. This is off to a great start already. Here we go. Okay, so what you need to know for the quiz, you have the copy of the quiz. So as long as you can fill that out, you'll be good to go. So it's got you have to draw the structure, you have to give me the 3-letter and the 1-letter abbreviation. For the quiz, you're not gonna have to give me any defining characteristics. So like polar, non-polar, charged, uncharged, you're not gonna have to tell me anything like that on the quiz. But you will need to know all of that about the amino acids. So not on the quiz, but you will need to know it before you get to the test. So all right. So general structure of amino acids. If you've seen them before, you probably already know this. If not, here we go. So they all have this central carbon here. So you'll see it sometimes it's called like the central carbon, the primary carbon. Most often though, you'll hear it called the alpha carbon. So I think maybe on the next slide or two, we'll see how the carbons get labeled as we go, but this one will be called the alpha carbon. They all have an amino group, so this NH2. They all have a carboxyl group, the COOH. For the most part, they're going to have like this little hydrogen guy up here, and then they're going to have the side chain R, and then that R group down there is what's going to be different for each of the amino acids. So there's 20 common ones in the human body. So this is pro proteinogenic, I don't know. There's the word. If you see that word, that's what it means. It's referring to the 20 common amino acids. There are lots more amino acids. Um, don't worry about knowing those. Someone last year, the same someone that we talked about previously, that had previously learned the 20 amino acids and then decided not to study them, did decide to study the uncommon ones. Um, You don't need to know those. Don't waste your time. If I ever am going to ask you a question about one of the uncommon ones, I'm going to give you the structure of it. So don't waste your time. Anyway, these are the building blocks of peptides and proteins. So when we get to next chapter, we're going to string together these amino acids to make these long like polymers of amino acids that we call peptides and proteins. So general structure though, amino group, carboxyl group, R group, alpha carbon. All right. So the convention for identifying the carbons, and this will come into play when we get to looking at 3D protein structure when I get back from my trip. It's very similar to, well, it's based off of the normal numbering system. So y'all just got out of organic, so you know this. Your C1 is going to be your highest priority carbon, which in this case would be this carbon here. So you go 1, 2, 3, 4, 5, 6. And amino acids, though, we're not so much worried about the carbon that's participating in the carboxyl group. We're more worried about the central carbon and then the R group. So they give us another naming system because why wouldn't we want more of that? So the alpha carbon they define as the central carbon on the amino acid, and then it goes down the R group. So this would be your R group for lysine. So you start out, here's your alpha carbon, there's your carboxyl group, there's your amino group, there's the hydrogen, and then there's your alpha carbon, the central carbon, and then you go down the R group. So alpha, beta, gamma, delta, epsilon. It's been a minute since okay. Looks like an E, so going for it. Anyway, so that's usually how, if we're going to be like talking about a particular R group and how it interacts with something later on, we're going to use this kind of notation rather than starting at C1. Also because C1 can kind of change depending on what the R group is and that kind of stuff. So we'll just use this one so that it's always the same. Alpha carbon is the central one, and then beta, gamma, delta, epsilon, and so on will go down the R group. Make good sense? Yeah. We're gonna have lots of new ways to name things this semester. It's so fun. Love that for us. So most of the amino acids are gonna be chiral. They're tetrahedral and they have two stereoisomers, which are enantiomers. So yeah, it's these two here. So these are the two ways you can draw alanine. So we'll use the L and D system to sort of specify which one we're looking at. We really won't have to worry about this too much. But when we get to occasionally it'll be relevant for protein structure. But we won't have to worry about this too much. But anyway, so the L is when your amine group is on the left side of the molecule. So if you're looking at it and the amine is drawn on the left, you're in the L configuration. And then if you're looking at it over here and the amine is drawn on the right, that's the D configuration. So pretty straightforward there. So there's your little, 3D model of it. There's it with the stereochemistry drawn with your wedges and dashes, and then there's just the normal bond. So in each of these, though, you've got your amino on the left for the L configuration, and your amino on the right for the deconfiguration there. And I believe I thought I had this on this slide, but it is not. Let me check before I tell you incorrectly. Just kidding. I'm like 99% sure we'll revisit this in another time when we get to proteins, but it's the like 99% of the time you're going to have the L configuration in the human body. But we'll revisit that later. All right, we good with L and D. L is left, and then the other one is right. So, love an alliteration thing to help us remember. Oh yeah, and then glycine is an exception. So we'll see all the structures for them here in a second. But glycine's R group is just a hydrogen. So then you've got your central carbon, your carboxyl group, your amine group, but then you've got two hydrogens, so it's got two of the same like substituent groups there. So then it's not going to be chiral because two of your substituents are the same. So glycine, not chiral. Here are the structures of all of them. So I like this figure. This one's not from our book. I think this is from the book that I used for the nutrition biochemistry class. But it highlights the R group. So this part of the molecule is like always going to be the same with the exception of proline, which we'll get to here in a couple of slides. But you've got your amine group, you've got your carboxyl group, there's your carbon, there's your hydrogen, and then the highlighted part is the R group that's going to change for each of them. So I like how this one has it drawn out. So if you're trying to like study for your quiz, the key's up on Canvas, so that's one way to do it. But if you don't want to look at my chicken scratch, here's a this is basically where I copied it from. So if you want to look at a prettier version, there she is. And it's got it nice and highlighted for you. So I think it's a pretty friendly one. And so it's got all of the amino acid grouped into different sections here that are kind of boxed off. So here we've got our nonpolar, aliphatic, R groups, aromatic ones, positively charged, uncharged, negatively charged. If you go to different textbooks, or if you're looking on Google or looking in your MCAT books or whatever, there are a billion different ways you can group amino acids. So this is one way we can group them, but if you look somewhere else and they've got them grouped different ways, that's fine. There are lots of different categories that you can make with different amino acids depending on like what context you're thinking about them in. This, for the most part, is how we're going to think about them because this is what's relevant to thinking about the 3D structure of proteins, which is where we're headed. But again, if you're, looking in some other book or some other resource online, they may have different categories that they place them in, and that's perfectly fine. But we're going to mostly think about them like polar versus non-polar, charged versus uncharged, because that's what's going to matter when we get to proteins. All right. So now we'll look at all the different little categories. So this is going to be the non-polar aliphatic R groups. So got this little piece of our table here. So we're grouping them by their R groups, right? Because everything else is the same. So the R group is going to sort of determine what these like properties are. So for this group, the R groups are going to be hydrophobic. They don't like water. They would prefer to not be in water. And so what we'll see is the hydrophobic effect, which we looked at with the last chapter, which is where all of the, like, bless you, all of the hydrophobic things will kind of like group together and sort of try and keep themselves away from water as much as they can. This will happen with these amino acids too. So if you've got a bunch of hydrophobic amino acids all like string together in a protein, the protein's going to like kind of try and fold and contort itself to get all of those hydrophobic ones together, sort of in like a little knot. It's not going to form a micelle per se, but it's going to kind of try and do that as best it can as a protein. And we'll see that when we get there. So don't worry too much about that right now. Right now, just know these ones are hydrophobic. Their R groups don't like water. Some exceptions, glycine really isn't that hydrophobic. Its R group is hydrogen, which, by itself is, I guess, would be hydrophobic. But as an entire molecule, you've still got this carboxyl group and this amine group. There's just really not anywhere else to put glycine. So if you're like ranking them in terms of hydrophobicity, glycine is going to be at the bottom of the list. It's not very hydrophobic, but we can't really call it super polar either. Anyway. And then proline is also in this group here. She's special. We will revisit her often in the next couple of chapters. So it is making this little ring structure here. So your amine group, so what's normally like this NH3 plus over here, the nitrogen is actually going to bind to the R group of proline and make this ring. So it's gonna have a really rigid structure, which is gonna matter when we start looking at protein folding. But for now, just know that she's nonpolar. It's a ring. The nitrogen is gonna be not an NH3 plus. Um, so that's her. Question so far? Feeling good. All right. So these are going to be our aromatic R groups. These are going to be relatively nonpolar. Hopefully you remember that from your aromatic things. It's a lot of carbons and hydrogens, so generally they're not very polar. Phenylalanine here. So there's its R group. It's going to be about as nonpolar as you can get as an amino acid. You've still got these groups up here, but the R group, it's all carbons and hydrogens, and we got a ring. It does not want to be around water. Tryptophan is this one over here. It's slightly polar, but still not super polar. You've got this like nitrogen here, but you've got all these rings and carbons and hydrogens and all that. So it still is not going to love water, but it's going to be a little polar. And then tyrosine is going to be the most polar of our aromatic R groups, because it's got this OH group down here. So that's going to be able to participate in hydrogen bonding. And it's going to kind of offset a lot of the hydrophobicity of this ring there. So we couldn't really group these in a polar versus non-polar category because they're kind of in between. So we make them their own category of aromatic. So there you go. Yeah, they can all still, so even though tyrosine is more polar and this one's a little polar because of their nitrogen and oxygen groups there, they can still all contribute to the hydrophobic effect. So especially this one can kind of be a little bit of like a switch hitter because it can hydrogen bond if it needs to, but it also can participate to the hydrophobic effect because it's got this ring there. And then later, several chapters from now, we're going to look at like protein analysis, so kind of how they measure proteins and analyze them in labs. But one thing that we'll see is that these aromatic groups can absorb UV light at 280 nanometers. So we'll revisit that when we get to protein analysis. But when you've got a protein or something that's got these aromatic groups in it, it's an easy way to analyze them and quantify them. Good here. Sweet. Wait, okay, that was it. So now here's our polar uncharged R groups. So these are going to be more hydrophilic. So they're still uncharged. Charged is going to be even more polar. But these ones are polar even without a charge on them. But they're not charged, but they're polar. So we give them their own little group here. So these are going to be way more hydrophilic than anything that we've looked at so far. The R groups can all hydrogen bond somewhere or another. And then, yeah, sort of the exception to this one is cysteine. So it's got the sulfur here. So it's not gonna really hydrogen bond so much. But it's still polar-ish, but less so than the other ones. Oh, y'all can't really see cysteine that great. Well, what is covered up by our dear sickly friends is a CH2, and then down here is the sulfur hydrogen. That's really the important part anyway. So all you're missing is a CH2, and then everything else looks the same as all the rest of them. But the important thing about cysteine, and this is much important, is that it can form disulfide bonds. So if it like, so you got like a big old protein and it decides to like fold in half, and then you end up with cysteine here, cysteine here. So you've got like sulfur, hydrogen, they're gonna form a bond. And then that's like a covalent bond that's going to keep your protein structure together. So cysteine is important for the 3D structure of proteins for sure because of the disulfide bonds that it can form with its little sulfur group. Did y'all look at disulfide bonds at all in OChem? It's okay if not. Well, when we get to protein folding, we'll look at how they form and that kind of stuff. So it's just a sulfur-sulfur bond. That's it. Disulfide, two sulfurs. That's it. That's all you need to know for now. We'll look at how the bonds form and stuff later. But know that cysteine can form a disulfide bond. If you don't know what a disulfide bond is, that's okay. We'll learn that later. So now we've got our positively charged R groups. So I feel like this confused a lot of people last year, so I'm going to try and make it a little more clear this year. So we're going to have positively charged and negatively charged R groups, but this is going to be at pH 7. So here in a minute, we're going to look at the ionization of amino acids as we change our pH values. But when we're trying to group them like this, we're going to think about it at neutral pH because that's what they're going to be like in our bodies for the most part. So these are going to be our positively charged R groups when they're at pH 7. There is a time where it will not be positively charged, and that is okay. We are going to call it a positively charged R group because we're going to think about it in biochemical conditions, which would be pH 7. We'll manipulate them later, but in general, when we're not trying to manipulate them, they're going to be positively charged. Does that make sense? Okay. See any no's, so. All right, so these are going to be very polar, very hydrophilic. They've got a charge on them, which is going to make them super polar. So they're going to love to be in and around water. They're not going to be participating in any kind of hydrophobic interactions going on. So they love being in the water. They're happy about it. It's a great day. Histidine, though, in this case, so this guy over here, he's special. And that's because the pKa for this R group, which we're gonna look at what happens when we're at different pKa's and stuff. But its pKa is it's around 7. I think it's like 6.8 or something like that. So in biological conditions, it can be positively charged or not. So it can act as a proton donor and a proton acceptor, which when we get to enzyme reactions is going to be very important because it can sort of act as like an acid or a base in biological conditions. So a lot of these amino acids can do that at certain pHs. So they can kind of act as buffers, which we'll look at probably on Monday. But histidine is really the only one that can do this in biological conditions. So that makes it fun. All right. Questions there? All good. Okie dokie. So negatively charged are groups. Same thing here. We're gonna base this off of them being at pH 7. So if we are moving around in pH, it might not be negative anymore, but we're gonna think about it in biochemistry conditions. In which case it's gonna be at pH 7. These will be negatively charged. These are also very polar, very hydrophilic. They've got that charge on them. It's going to distort the electron density, all that good stuff. So it's going to love to be around water. These, when you're going right now, you may not recognize it, but when you go to start memorizing stuff, these are the hydrolyzed forms of asparagine and glutamine. So you may recognize that. If not, that's okay. You don't have to. And they're the deprotonated forms of aspartic acid and glutamic acid. So as we talk about these, depending on what condition they're in, so right now I would call them aspartate and glutamate, but depending on like what figure we're looking at, or if you're reading it in the textbook, when they get protonated, so you have like your hydrogen there, a lot of times rather than say, oh, it's the protonated form of glutamate, they'll just call it glutamic acid because now it looks, it's in its acidic form. So I didn't want that to be confusing. If I ever say like aspartic acid, you're like, what the heck is that? It's just the protonated form of aspartate. All good. Sorry, I know this is like watching paint dry, but it's got to be done. Okay, uncommon amino acids. You do not have to memorize these. I would not recommend you spend any time on this. Let me make that abundantly clear. Uh, apparently it wasn't last year. You do not have to memorize these. Most of these are going to be modified versions of the common amino acids. So they'll have like a base structure of one of those like 20 common amino acids, and then after the amino acid is made, and a lot of times it'll even get incorporated into a protein. And then some kind of modifier will come around and do something to it. So yeah, so after protein synthesis, it can also happen during protein synthesis. So as you're like linking the amino acids together, it might throw another R group on there or something. And yeah, a lot of times these will actually be temporarily modified to change protein function. So protein may have a particular function, but then it needs to, go off and do some little side mission, but it ain't got the equipment for that. So your body will just be like, here you go, here's you an extra little sword. Go off and do your mission and then come back and then we'll take the sword back. I don't know. Like thinking of my husband playing these video games where he gets like little side quests. Anyway, so it may give it some extra little oomph to go do something it needs to do, and then when it's done doing what it needs to do, it'll give up the little oomph. Um, so and then some of these are free metabolites. Don't worry about that for now. We'll look at that at the end of the semester when we get to metabolism. We all cried together. So these can get really complicated. So here's like a pretty simple one that I think we don't talk about until we get to biochem 2, but it's 4-hydroxyproline. So you're just adding like a hydroxyl group over here to proline. So on C4 you're adding an OH group. Big whoop. But then you come down here to this guy and it's like, oh my goodness, that doesn't even look like anything that I recognize at all. So ain't no telling. I think that one is maybe 4 different amino acids that have all come together. Anyway, we don't need to know it. It doesn't matter. But some of them simple, some of them not simple. Anyway, but they do exist, so we have to talk about them. Okay. How are we? Oh, we still got time. Okay. We're gonna start amino acid ionizations and titrations today. So this is why we had to go back and learn about water. I know we weren't excited about it, but this is why. Because we had to remember what titrations were before we could start trying to do it with an amino acid. So here we are. Yay for us. Okay, amino acid ionization. So kind of like we've been hitting at so far, your amino group, so that NH2 or NH3 plus, whichever way we were looking at it, the carboxyl group, so the COOH or COO minus, and several of the R groups for the amino acids are ionizable. This means they can be neutrally charged sometimes, maybe they end up being negatively charged, maybe sometimes it's neutrally charged, and sometimes it's positively charged. Lots of different ones that we're all going to get to know before the test. Yay. But this means that they can act as weak acids and weak bases. So that means that they can act as buffers, which means we can look at them on a titration curve. Oh, good. Okay. Zoom will end in 10 minutes. Let me set a 10-minute timer. So whatever we get done in the next 10 minutes is where we will end today. Okay. How do I make that go away? Okay. All right, so Zwitter ion is going to be the dipolar ion. We'll look at a picture of this here in a second, but that's when your amino group is positively charged and your carboxyl group is negatively charged, so then they kind of cancel out. We'll look at a picture here in a second. Generally, and we're going to work several example problems with this before I leave you. Probably not today, but before I leave you for the trip, we will have done several examples with this. But generally your amino acids are going to be positively charged when they're in like, pH 2, and then they're going to be negatively charged when you're at like pH 11. But we'll work examples, but that's a general rule. So here's a pH dependence of ionization. So this is similar to the graph that we were looking at for titration. So you've got, one species at 100%, the other species at 0, and then as you start to add your acid or your base, they start to react and until you reach your midpoint when you've got equal conjugate acid base pairs. Anyway, similar thing there. So here we're dealing with this amino acid. It doesn't tell us which one, but we've got our R group. So we're on a scale of pH 0 here, so like the most acidic it could possibly be, all the way up to pH 14. So super basic here. So at pH 0, we're at the fully protonated version of whatever amino acid this is. So anything that can have a hydrogen is going to have a hydrogen. So what this means is our NH3 this will be NH2 later, but right now it's NH3 plus, so it's got as many hydrogens as it can handle. And our carboxyl group is also protonated, so it's got a hydrogen there. For the sake of this one, our R group is not ionizable, so it's just going to stay R the whole time. So as we're moving through our graph at pH 0, obviously everything is protonated, so this is going to be our acid, and then as we move up in pH, this would be our conjugate base. So it's going to be like the first little leg of our titration curve. So as we start to add base to our solution here, our conjugate acid is going to donate some of its, or it's going to be this one, sorry. Our weak acid here is going to donate its hydrogens to the strong base. And it's going to start forming this because it's giving up those hydrogens to form water. So we're not, shooting the pH from 0 to 14 in like 2 drops. So the concentration of this, our pink line, is going to start going down. Concentration of the conjugate base is going to start going up. Here we'll get to the midpoint. And then we keep going until eventually we're left with all of this and none of this. So we've got 100% this, 0% this. So this is all gone. Now we're left with just this. And then we keep going, we add more base. And then eventually we get to over here where now we still got all of this. But we're going to keep adding base. And so as we do that, now we're at a pH high enough where this amine group is going to start kicking off its hydrogens. So it's like, oh my goodness, we're getting so basic, I can't stand it anymore. And so it's going to start kicking off this hydrogen here, and it's going to form this compound here. So now we're just at NH2. So this would be the fully deprotonated version of this amino acid. So we keep adding our strong base, and this hydrogen is going to get kicked off to go make water with the strong base. And so we start forming this. So this guy is going down while this guy is going up. You reach the midpoint where you've got equal amounts of both of these, and then you keep going, and then we end up with more of this and less of this. And then we get all the way to the end where now at pH 14, obviously all you're going to have left is this, and then some really heckin' strong base that you do not want to spill on yourself. And all of this guy is going to be gone once you get here. So same concept, just now with amino acids instead of H2A or whatever we were looking at. Good deal. All right. So we'll do an example problem here without our little graph. So I'm gonna walk you through this first one because it's a little wonky. But we're gonna draw the ionization states / reactions for glutamate. So if I'm gonna give you a problem like this to do on a test, I will give you the pKa values. You do not have to memorize the specific pKa values for all of the amino acids. On Monday, we'll look at a table where you can make like some generalizations that are gonna help you. A lot of people it helped with the MCAT, so I was like, big win for that one. But anyway, we'll look at some generalization like groupings that you'll have to know. But if I need you to give me like the specific pKa values, I'm gonna give you those. You don't have to memorize those. Okay, so we're gonna draw the ionization states / reactions for glutamate. And then we'll include a possible pH value for each of the states, and then we're given the pKa values. So how to start this? What I would recommend, so you've got, probably not yet, but by the time you take your test, you will have all of the structures of the amino acids in your head. I cannot speak. So you'll have all the structures in your heads. You'll know, like, okay, let me flip through the tabs here. I see glutamate. And then I recommend starting with either the fully protonated or the fully deprotonated version because we're wanting to draw all the states, right? So every single ionization it's got, we've got to draw it and we've got to show it, going to the next protonated or deprotonated state. So I find it easiest to either start at like pH 0 and work your way up or start at pH 14 and work your way down. I prefer to start pH 0. I don't know why. It just works for me. If you'd rather start at pH 14, that's also fine. So our structure for glutamate, we've got a carbon. Here's our carboxyl group. There's our little hydrogen. There's the NH3 plus, and we're at pH 0 right now, so that's going to be our fully protonated. So we're going to have the hydrogen here. We're going to have this one protonated. And then our R group is CH2, CH2, COO. And then again, we're at like pH 0 down here. So we'll just say pH, we'll say 1. 0 seems extreme. So we'll say pH 1. So there is what the structure of glutamate would be. So this would be like glutamic acid, because it's the protonated R group. So that's what the structure would be there. Does that make sense? You just anything that can take a hydrogen, you're going to add a hydrogen to it. So then it gives us the pKa values. So for the alpha carboxyl group, which is going to be this guy up here, it's 2.10. For the alpha amino group, it's 9.47. And then for the R group, which would be this guy down here, it's 4.07. So if we're thinking we're starting at 1 and we're going up to 14, what's the first thing we're going to run into? What is the first number you would hit between 0 and 14 of these options? 2, thank you. I was like, oh no. Okay, so this is the ionization we're going to show first. So we'll do our little arrows here and we'll say pKa 2.10. So we're going to show the reaction that would happen at that pH pKa value. So we'll go ahead and draw. We said that this was for the alpha carboxyl group. So everything else is not going to change. We're going to leave everything else just the same. So NH3 plus. I do not know why it is doing all these little jumpy things. That's what I get for buying the $15 pencil. This is wonderful. H2CH2COOH. All right, so none of that changed. That stayed the same from the last one. We're dealing with our alpha carboxyl group. So what's going to happen when we go above the pKa for that alpha carboxyl group? I heard somebody whisper. I don't know who it was, but yes, we're going to deprotonate it. So I'm going to draw it in red here. So we get COO minus. So that's what's changing there. Make sense? Great. Then the next one we'll come into contact with. So after 2, oh goodness, it's terrible. pKa 4.07. Is that even like, can you even see that? Okay, a little bit. Anyway, it's pKa 4.07. And what's going to change there? Which one? This one? Yeah, the R group. So that's another important, that's something that a lot of people will trip up on with these. You got to make sure you're looking at the pKa for whatever group you're looking at. So the 2.10 pKa correlates to the alpha carboxyl group. So that's why we kicked off the alpha carboxyl